All right, anybody have any homework questions? Sure, sure. Do you happen to have it with you? Anybody have rigid body kinematics problems? Yeah, the first one. Can I use it? Okay, so rigid body kinematics, number 4. This is one with a carousel with a radius of 6 meters. Um, and so we have this thing rotating around with a constant angular velocity of 0.8 radians per second. And the seats move up and down according to the position function. According to the function y equals 0.5 times the sine of t. Okay, so you have, like the way a carousel works, the horses or whatever are going up and down as it rotates around this way. And so you have the things moving through a motion like that. They're going around and they're also going up and down at the same time. And so we want to figure out some things about the motion. And we want to do it for a kid who's sitting all the way at the outside, and we also want to do it for a kid who's a little bit closer. So this distance then is 4 meters. And I'll think of this as the point A, and this is the point B, the closer one. So we want to figure out the greatest speed, the greatest acceleration magnitude. All right, well, let's come up with expressions for the velocity of the kid and the acceleration of the kid. So velocity of the point A relative to the ground, that's what we're looking for, is equal to the velocity of A relative to, you can think of that as relative to like sort of, let me describe this a little better. So let's say that first we're looking at the kid sitting at the point A. Okay, so to figure out the velocity of the kid who's going up and down above that point A, let's figure out the velocity of the kid relative to the point, to the ground is what we're looking for. And we'll do that as the velocity of the kid relative to that point A, plus the velocity of that point A relative to the ground. And if if we think of the circular motion in a coordinate system with the x-axis this way and the y-axis is going to be pointing up, and that means that we would have to have the z-axis going this way. And here's our point A. The rotation is like this, and so the velocity vector is this way. The magnitude of the velocity is the absolute value of the angular velocity times the distance from the center of the circular motion to the point, r. And so that is equal to 0.8 times 6. So that's 4.8 meters per second. And that's pointing in the positive z direction. So the velocity of that point A is 0, 0, 4.8.
So why is double 0? Why is it 0, 0?
Well, so this problem has stuff going on in the y, z, x, y, and z directions. And so we're going to have 3 coordinates or 3 components for all our vectors. So that's 0 for x, 0 for y, and then 4.8 for z. Okay. And that's the velocity of A relative to the ground. Now we have to calculate the velocity of the kid relative to A. And you can think of that as, that's just going to be moving up and down. So you can think of that as 0 time derivative of, the time derivative of the y position, 0. This is just the time derivative of the position. And so that's equal to 0.5 cosine t, 0. And so you can think of the velocity vector of the kid relative to the ground as being equal to 0.5 cosine of t, 4.8. And now we're just looking for where this is maximized. Well, what t value is cosine of t a maximum for? Yeah, 0. So that's a max at time equals 0. And so the velocity max is 0.5, 4.8. And the speed is 0.5 squared plus 4.8 squared square root. Any questions about that? And the acceleration is the same idea. So the acceleration of the kid relative to the ground is equal to the acceleration of the kid relative to A plus the acceleration of A relative to the ground. There's no tangential acceleration, there's only centripetal acceleration. And the magnitude of the centripetal acceleration is omega squared r. So that's 0.8 squared times 6. That is 5.04. 3.84. 3.84 meters per second squared. Okay. That's the magnitude, and so the centripetal acceleration vector is in the positive x direction, so that's 3.840, and then 0 for z too if we're doing it in 3 dimensions. And that's the acceleration of the point A. And then our position double dot is the acceleration of the kid relative to A, and that's equal to 0, negative 0.5 sine of t, 0. And so the acceleration of the kid relative to the ground is 3.84 negative 0.5 times sine of t, 0. Where is sine maximum? Yeah. So the maximum absolute value is when time is equal to pi over 2. And at that point you get 3.84 for x, negative 0.5 for y, 0 for z. And so the maximum acceleration is the magnitude of that 3.84 squared plus negative 0.5 squared square root. I won't put anything with 3 dimensions like that on the test, but that's how you would do a problem like that. Any other homework questions? Yep. A little bit longer, yeah. So I would say it will be up to 2 hours, maybe 2 hours for the last people who were there. I'm still not planning to make it, feel rushed or anything. I think, you know, there'll definitely be people done in less than an hour, I would say. But yeah, it'll be, I don't know, maybe 50% longer or something than, uh, just so I can fit a couple other problem types in. Yep. No, it's, well, there will be more new stuff than any individual older topics, but I'd say it'll be at least half old stuff.
So for like the new stuff will be like today, would that be on the final exam?
Yeah, right. Um, any other questions, Tristan? Yeah. 6A and B? I'm missing that one, I think. Oh, okay. Thanks. Okay, so the rectangular object shown below has a mass of 5 kilograms. A length of 1 meter, and a width of 0.25 meters. And it rotates about the hinge at C. And this is the point A. The angular position follows the function theta of t is equal to 4t cubed minus 10t. And we need to calculate the mass moment of inertia about C, the mass moment of inertia about A, the velocity vector of A at time equals 5 seconds. So when time is equal to 5 seconds, we're going to assume that the position looks like this. And we're going to figure out what like angular velocity and angular acceleration based on this function at time equals 5 seconds, and acceleration too. Okay. So part A, what's the mass moment of inertia about C? C is the center of mass of that body, and so we're not going to have to use the parallel axis theorem. Yeah. It's in kinematics. I mean, you could, yeah, it's in the thing on kinematics. So C is the center of mass of the body, and so all we're going to use is the formula that says the mass moment of inertia of a rectangular shape is equal to 1/12 times the mass times the length squared plus the width squared. So that's 1/12 times the mass of 5 kilograms times 1 squared plus 0.25 squared. And that is 0.416 repeating times 1.0625. Can someone calculate that? 0.442 kilogram meter squared. And then for part B, we're going to calculate the mass moment of inertia about A. About the point A on the right. That one is not at the center of mass, so we're going to have to use the parallel axis theorem. So the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass. That's what we just calculated. Plus the mass times the distance squared from the center of mass to the point. And so that's 0.442 plus 5 times the distance from C to A is 0.5. So this is 0.5 squared. And so that is 1.6 what? 92 kilogram meter squared. Any questions about that when you use the parallel axis theorem or anything? Yeah. Yeah, I'm not done with this yet, but yes.
Most of the time, like if it's on the center of mass, you have to use the pair of what.
Always, yeah, the parallel axis theorem. So if it's in the center of mass, you don't have to use it. If it's about any other point, you do. Okay. Okay, and now what's the velocity vector of the point A at t equals 5 seconds? Okay, so well, to find the velocity vector, we're going to have to use circular motion. The velocity is, the magnitude is going to be equal to the angular velocity times r. And to figure out the angular velocity, we know that the angular position as a function of time is equal to 4t cubed minus 10t. And so the angular velocity as a function of time is just equal to the angular position dot. And so that is 12t squared minus 10. Now we can plug in time equals 5 seconds. And omega is equal to 25 times 12, 300, minus 10, so 290 radians per second. And since it's positive, we know that it's moving counterclockwise. That point A is moving in a circular path, counterclockwise around the center. Because if omega is positive, that's counterclockwise. If it's negative, it's clockwise.
So basically the direction is
of the velocity, yep. So the velocity vector is like this. This is the body. Right. And so now we can say that the speed of that point is equal to the absolute value of omega times the distance from the center of the circular motion to the point. And so that's 290 times what's the distance from the center of the circular motion to the point? 0.5. And so that's 145 meters per second. And since that's in the positive y direction, using this coordinate system, the velocity vector of the point A is 0, 145. Yep. What does it say? It says that? Ah, shoot. Okay. Okay. Right. Okay. So we're going to have to. All right. So horizontal is what we're calling 0. So everything is right up until this point. But now we're going to have to think about what orientation this thing is in. Okay, so we're also going to have to figure out what omega or what theta is at 5 seconds. So theta at time equals 5 seconds is equal to 4 times 5 cubed minus 10 times 5. What's that? 125 times 4 is 500. So this is 450 radians. So we can take off as many times, anytime you go 2 pi radians, you end up where you started. So how many 2 pi radians can you take out of 450? Basically we're just looking for the remainder after you take out all the 2 pi radians. What? So 2 pi is 6.28, take out a bunch of those. I'm trying to figure out what's left over after you do all the full rotations. You know what I mean? That's too big. So it's going to be 450 divided by 2 pi without the remainder. 71.69. And then 0.61. Okay. That's how the last, and so the last one is 0.6197 of a rotation. Okay, that's the remainder. Okay, so, and then that times 2 pi is the angular change. So what's 0.6197 times 2 pi? Okay, so so the angular position is 1 point, tell me one more time. Okay, 4, 6, 8 radians past the starting position. And so let's figure out what that is in degrees. I can just picture that better. So multiply that by 180 and divide by pi. 111.55 degrees. And so we are talking about this. So here's our point C. Here's the vertical. Here's A. And this angle is 21.55. And the circular path of that point is this. Okay. It's rotating this direction. And so the velocity vector is this way. The speed is still going to be, okay, so the speed is still going to be equal to 450, it's still going to be equal to the absolute value of the angular velocity times r. And so that's 450 times 0.5. Yeah, 290. And so that's 145. And now we have to figure out how to represent this direction. Well, if this is the coordinate system, then a vector in this position, in this orientation, is at an angle of what we just found, 111.55 positive. And then a vector going in the direction we want, this angle, this is in the same direction as V, that's another 90 degrees counterclockwise. And so I'll add 90 to that. And so this is equal to 201.55. And so that velocity vector is 145 times cosine of 201.55 and 145 times the sine of the angle 201.55. Can someone calculate those two components? Okay. 2.6? Okay, so that's meters per second. So that's the velocity vector. The only thing that's harder about this problem than other problems is that you have the funky angle for so when you figure out the magnitude of the velocity and the acceleration vectors, you have to figure out these funny unit vectors to multiply it by. And then to calculate the acceleration, so this is the point C, the part C. Part D, we're trying to figure out the acceleration. theta double dot is so that was 12t squared. Now we got 24t. But now this is the second derivative, so it's just going to be 0. You know, we're just taking the time derivative of this, of 12t squared minus 10. So we just have 24t. And then when time is 5 seconds, you know, this is going to be our alpha. And alpha is equal to 24 times 5 is 120. Radians per second squared. The circular motion looks like this. We have a positive value for the angular acceleration, so omega is that way and alpha is also that way. Our velocity was this way. This is the point A. This is the velocity vector. It's speeding up, so this is also the direction of the tangential acceleration. The centripetal is toward the center. The magnitude of the centripetal acceleration is omega squared r. And at time equals 5 seconds, omega was 290. So 290 squared times 0.5. Can someone calculate that? Some huge number. 43,000? 42,050. And now we have to figure out how to use cosine and sine to get it in the right direction. Well, we know that a vector going this way is 111 point whatever we had before, and a vector going this way is 90 degrees from that, and then the vector we want is 90 degrees from that. These are all 90 degrees apart, and so the theta here for cosine and sine is 111.55 plus another counterclockwise angle of 90 plus another counterclockwise angle of 90, and you get 291.55. And so the centripetal acceleration is 42,050 times cosine of 291.55, 42,050 times sine of 291.55. Can someone calculate those? That it should, both components should be smaller than 42,050. 15,445. Okay. And then the y component. Okay. And that's the centripetal acceleration. And then the tangential acceleration is in the same direction that we had before, for the velocity. The magnitude is equal to the absolute value of alpha times r. Alpha is 120. So this is 120 times 0.5. 60 meters per second squared. And then, so the tangential acceleration is 60 times cosine and sine of 201.55. And what do you get for those two components? Okay. 0.0. And then just add those two together for the total acceleration. So the acceleration of that point A is, just the sum of those, whatever it is, centripetal acceleration plus tangential acceleration. So I guess you would say there's sort of two conceptually, well, one is conceptual, one is kind of mathematical. Conceptually, to do this problem, you have to remember that if you have the angular position expressed as a function of time, you can come up with the angular velocity and angular acceleration lower down by taking time derivatives of that. That relationship always holds between those. And then once you have the angular velocity and angular position, you're just doing circular motion. But the mathematically tricky thing in this problem is you weren't dealing with vectors along the axis directions. You're dealing with funky axes. And so, you have to use cosine and sine to come up with unit vectors in the directions of these vectors. Any questions about that one? Any other homework questions? Yep. 10. 1, 2. Yeah. So we're dealing with this arbitrary shape. And the point A is here, and the axis of rotation is here. And we're given that there's a distance between these 2 points of 0.3 meters. And so this point A is moving in a circular path around the axis. So, its circular path is something like that. And we are given that this problem sort of works in reverse of the way we usually do these. The tangential acceleration vector, we're told, is 0, -4. So the tangential acceleration is this way with a magnitude of 4 meters per second squared. And the velocity vector is in the positive y direction with a magnitude of 10 meters per second. And we need to figure out the angular velocity and angular acceleration, and whether it's speeding up or slowing down, that kind of stuff. Well, the angular velocity has to be this way if the velocity is up. And the angular acceleration has to be this way if the tangential acceleration is down. And we know that, and so what that says already is we know that omega is going to be positive because it's counterclockwise, and alpha is going to be negative because it's clockwise. And now we need to figure out the magnitudes. So first use the fact that the speed is equal to omega r. And so that says 10 is equal to omega times 0.3. And so omega is equal to 10 divided by 0.3. So 33.3 repeating radians per second. And now put in the sign. You know that it's positive because you can tell from looking at the directions of these things that this is counterclockwise. And then the magnitude of the tangential acceleration is the absolute value of alpha times the distance from the axis of rotation to the point. And that says that 4 is equal to alpha times 0.3. And so alpha is equal to 4 divided by 0.3, 13.3 repeating radians per second squared. And this one is negative because that rotation is clockwise. And then it asks some stuff. Is it speeding up or slowing down? It's slowing down because velocity and acceleration are opposite. Angular velocity and angular acceleration are opposite. For either of those two reasons, you can tell that it's slowing down. And then the total acceleration, the total acceleration of A is equal to the tangential plus the centripetal. We weren't given the centripetal acceleration, so we're going to have to figure that out. The centripetal acceleration goes this way. The magnitude of the centripetal acceleration is omega squared r. So that is 33.3 repeating squared times 0.3. What's that? 333.27 meters per second squared. Actually, that's 3 repeating. Let's just round off error. And then the direction is negative x. So the centripetal acceleration vector is negative 333.3 repeating 0. And so the total acceleration of the point A is negative 333.3 repeating 0, plus the tangential acceleration that was given, 0, negative 4. And so the total acceleration is negative 333.3 repeating, negative 4 meters per second squared. Any other questions about that one? Okay, that's it.
When you get our